The population of Kenya was 19.5 million in 1984 and was 32 million in 2004. Assuming the population increases exponentially, find the formula for the population of Kenya as a function of time. Then, using logs, find the doubling time of Kenya's population. First of all, here let's write the formula of exponential growth, which is y equal with a time 1 plus r, the factor b is 1 plus r, in exponent t, because we are looking in function of t. We are looking for the time. So now, here let's plug in the known information. The initial value here, a, is equal to 19.5 million. 19.5. So let me write 19.5. And then 1 plus r, we don't know the rate, so the rate we are going to write in the way how it is, 1 plus r, because we are looking first to find the rate. We need to find the rate first. But from 1984 to 2004, there are 20 years. That's why t is equal to 20 years. And for 20 years, we are looking to know how much was increased the population. From 1984 to 2004 was increased to 32 million. So this is the population, how much it was increased from 1984 to 2004 for 20 years. And now this equation we want to solve for r. But first of all, we are trying here to divide by, to make a little bit simple this equation, we will divide by 19.5 both sides, by 19.5 both sides, and we're gonna get, we divide both sides by 19.5, and now let me take a calculator here, and let me try here to divide the 32. 32 divided by 19.5, 19.5, we get 1.64. So it's 1.64. And in the other side, if I divide the other side by 19.5, this side 19.5 divided by 19.5 is going to disappear. What remains 1 plus r. 1 plus r in exponent of 20. So now what I'm going to do here, I'm going to log both sides. If we are logging both sides with a logarithm, so log 1.604, log of 1.64, 1.64, and in the other side is equal with a log of 1 plus r, of 1 plus r. Everything in exponent 20. So here is exponent 20. And let me first of all find out the log. What is a log of 164? Is 0.215. So I'm approximating this number with 0.215. So when I'm finding a r is not going to be exact value because I am approximating those numbers. I am truncating the lots of decimals here. And according to the rules of the logs, this 20 goes in the front here, goes in the front, 20 here goes, 20 time log of 1 plus r. And now because I have this 20 here, again I'm going to simplify this equation, so I'm going to divide everything by 20. I'm dividing everything by 20. And when I divide everything by 20, let's see what I'm going to get here. This I'm dividing by 20. And I'm getting 0.0107. So I have a 0.0107. 07 is equal with if I divide this side by 20, 20 is going to disappear. What is going to remain is going to remain a log of 1 plus r. So now it's a more simple equation than it was before. But this equation now I'm going to convert into the exponential form, and here is a base 10. And what I'm going to get, let me write a little bit better. This side I'm writing n plus r is going to be equal, because 0.017 is going to be the exponent, in 2 in exponent 0.0107. And now from here I'm trying to find out what is going to be r. So r was going to be. So now let me take a calculator. 107. Let me find here, for example, what is going to be the exponent 10 is 1.0250. But because I have this side 1, I am subtracting by minus 1 this side and this side here. And let me subtract by minus 1. And I'm going to get, this is going to be 0.025. Let's make 0, because I'm approximating 0.25. So now I got this value here. But if I want, for example, here to find an equation that instead of the r, I'm plugging here, for example, y is equal to, the initial value was 19.5. So I want to find one equation that can model the increase, the growth of the population in Kenya. Is going to be 1 plus r. 1 plus 0.025 is going to be 1.025. So the factor b is going to be 1.025, and everything is going to be in the exponent t. So based on this function, now we can find the population for how many years is going to increase each year. For 10 years, 100 years, we just plug in here. If the population grows exponentially with this equation, then we can find out how much is going to be the population after 100 years or 50 years or whatever we want to know. And the graph of the function is going to look similar with this function here, what we have. And for example, what we are looking here, the next it says, then using logs to find the doubling time of Kenya population. They want to find when it's going to double the population, which year is going to double. And according to the graph, I know here is in 1984 is a 19.5 million. And if I'm going up here after 28 years from 1984, it's going to double around the 39 million, because around 39 million is doubled on 19.5. And which means after 28 years, and from 1984 plus 28 years is going to be 2012. But now let us see here, for example, if we are going to double, it's going to be 39 million. So let me write here 39, around 39 million is going to be equal. So we are solving analytically, and graphically we already know in 2012 is going to double graphically. But let's solve it analytically and see, do those two values are similar. So now here is a 19.5 and is and we already know this b factor is 1.025, 1.025, and in exponent t. So we are looking to find the time. How much time is going to double the population? We divided this equation by 19.5 both sides. If we divide by 19.5 both sides, I already know this is going to be equal with 2. And 19.5 and 19.5 here, if I'm dividing, let me write here the division. What I'm using here just to signify this is a division. I'm dividing by 19.5. I'm dividing both sides. And what I'm going to get here, I'm going to get 2 is equal with 1.025 in exponent t. In exponent t. And now this one I can write in as a log, but this is a base. And what is going to happen is going to be a log of 2 of base 1.025 of 0.25, the base of 125 of 2 is equal to t. But now it's very hard now to find in a calculator this with this base, but this log we can convert into the common logs, and t can be equal with the log 2, the common log of 2 divided by common log of 1.025. So this can be a log of 2 divided by log of 1.025, log of common log of 1.025. So now these logs we can calculate in a calculator, and we're going to look at what we are going to get. And t is going to be equal. Let me write here as one fraction here. And let's use a calculator. So now log of 2, what is log of 2? Is 0.3. Let me approximate 0.3. So we are looking just, can we get around to 28 years? Does this correspond with the values in the graph? And then we already got log 2. Now we are going for the log of 1.025. Let me erase this number here. 1.025, and I'm getting common log is 0.0107. So it's 0.0107. And now finally let's calculate everything what's going to happen. 0.3 divided by 0.0107 is equal with 28. So the time when is going to double the population of the Kenya from 19.5 million to 39 million is going to take around 28 years. 28 years. So it's going to take about 28 years.